Hello everyone, welcome to this next video on complex analysis. In this video we shall see a result which is very famous and which is due to Green's theorem, and we'll use this result in this particular question taken from the paper 2009. So the question here is, if uxy be the real part of an entire function f of z, so we are given f of z, that is an entire function. What do you mean by entire function? That means this function is analytic everywhere on the complex plane C except the point infinity. So we are not taking the infinite complex plane, we are taking the complex plane to be a finite plane, right? And where this z, that is particularly a complex number. If C be the positively oriented boundary of the rectangular region R in R square, so basically what is this R or what is this C? That is, this is R square, this is x axis, this is y axis. Then they are saying we have a rectangle, say something like this. It could be placed somewhere else also, and the direction of this particular rectangle is taken to be in the this is positively oriented, that means this is taken to be in anti-clockwise region. So this is our C, this is particularly rectangle. So they are asking what is the this integral, what is the integral over the C of this quantity. So for that we would require this integral over C, and we'll convert this to the corresponding integral over R. So that means we'll convert our this single integration to double integration. For that we'll need Green's theorem, which relates the line integral around a simple closed curve C to a double integral over the plane region D bounded by C. So let us see the exact statement. The exact statement is that these are all the assumptions. What are they? They are saying C be the positively oriented, piecewise smooth, simple closed curve in a plane. So we have this, all these conditions are satisfied. This is simple closed curve, positively oriented, and it is smooth as well, right? Moreover, they are saying D be the region bounded by C. So we have this particular region which is bounded by this curve C, right? So this condition is also satisfied. Now they are saying L and M are functions of x and y defined on this region D, open region D. So we have this del u by del y and minus del u by del x. They are also defined on this region D, right? And having continuous partial derivatives there, and here the derivatives of this term and this term, that means the double derivatives, del 2u by del x del y and del 2u by del x square or del 2u by del y square, they are continuous. Why this is so? Because our function is analytic, that means this part and this part, they are analytic as well. And if a function is analytic, then all then their derivative of all order, they are continuous. So here we are saying it should have continuous partial derivatives there in that particular region D. If all these conditions are satisfied, then we would say our line integral L dx plus M dy would convert into this double integral, this one, right, where the path C is always oriented in anti-clockwise direction. So here particularly what we are given here, this quantity, so it would be we are given integral over C, the integral over C of the quantity del u by del y dx minus del u by del x dy. This thing is given to us. After applying this theorem, we would have something like this, double integral over the rectangle R, right? So now this is our M, sorry, this is our L and this is our M. So we would have the partial derivative of L. So we would have double derivative of this m firstly with respect to x, and here we are given y with respect to y, and secondly we would have here del 2u by del y del x. Now because these are assumed continuous, so that means this quantity and this quantity, and moreover we have this dx dy. So this quantity, they cancels with each other, so our result finally is 0. So this is as simple of a question if you know what is a green theorem and how to apply it. So the answer here is option number B. So I hope you understood the concept and this theorem. Well, that is it for this video. Thank you for watching.